Students, in this class we are going to see the concept of compensation techniques, and before going for the compensation techniques I would like to tell you what is the necessity of going for the compensation techniques. So if you see it clearly here, for the stabilization of the operating point Q there are two types of techniques. One is the stabilization techniques and other one is compensation techniques. So the operating point Q having the coordinates of VCE and IC, and in the last classes I told you your collector current IC is not constant, it is always a function of temperature, base to emitter voltage and beta also. So IC, collector current IC is a function of reverse saturation current IC naught, VBE base to emitter voltage and beta of the transistor. So as this collector current is changing with all these parameters, the operating point is also changing from time to time. So to keep this operating point at that position at what we have fixed there are two types of techniques: stabilization techniques and compensation techniques. Already we discussed the stabilization techniques. Under this we have discussed the fixed bias, collector to base bias and self bias. Out of all these biasing techniques, we concluded self bias, which is also called as an emitter bias, is the most popular bias because it has taken care of all the variations of this collector current with respect to IC naught, VBE and beta. But the problem here is in the stabilization techniques. Even though we are fixing the operating point and we are making the operating point stable, the main disadvantage of the stabilization techniques is feedback voltage. That means the amplification of the output decreases. So in all these techniques what we have done is we have used a feedback resistor. That means there is a connection from output to the input, so the amplification is actually decreases. So there is a loss of the signal because of the less amplification. So that's the reason, in order to avoid that factor here, we are going for the compensation techniques. Once again I would like to tell you, the major disadvantage of the stabilization techniques is the amplification of the signal decreases at the output because of the feedback from output to the input. If the loss of signal is much more, that means if you are sacrificing the amplification of the signal, then definitely we have to go for the most popular techniques, that is compensation techniques. Under this compensation techniques, we are going to use the devices diodes, transistors, thermistors and sensistors. These thermistor and sensistors are the temperature sensitive devices. So in this class, we are going to discuss in detail about these compensation techniques. Using these compensation techniques, we are going to compensate the loss you are getting in your stabilization techniques. Stabilization techniques is primarily meant for fixing the operating point, and they are also taking care of the temperature variation and base to emitter voltage and beta. But if you are taking this feedback resistor here, and because of the feedback resistor, suppose if you are taking a transistor like this is the transistor, and this is nothing but the collector and this is nothing but the emitter, and you are having a feedback resistor here. This feedback resistor is always taking the part of the signal from output to the input, so the net amplification at the output decreases. That is the reason we are using the compensation techniques now. So let me discuss the compensation techniques now. And if you take this circuit, as usual it is a common emitter configuration here, and RB is nothing but a base resistance, and RC collector load resistance. You are taking the output at the collector, and this is VBE, this is plus and this is minus base to emitter voltage here. So this is already I told you at the time of your self bias. Indirectly it is a self bias circuit. Self bias means which is also called as an emitter bias and much more famous also. So here the compensation we are providing for the loss of the signal using a diode. So if you see it clearly, we are inserting a diode D here, and which is forward biased by VDD. VDD is the supply which is forward biasing this. So the material should be the same for both transistor and diode because the variation should be same. Now this is the circuit actually compensating the change in VBE. So that's why this is the diode compensation. Diode compensation for which parameter? That parameter is nothing but VBE. Diode compensation for VBE based to emitter voltage. Now see the circuit, it's very simple. I am checking for the temperature variations. Suppose if the temperature changes, temperature increases, then automatically the base to emitter voltage also changes. Because already in semiconductors I know this diode voltage drop VBE always changes minus 2.5 millivolts per degree centigrade. That means per degree centigrade 2.5 millivolts decreases. That is the change of your VBE. So this change should be compensated using a diode which is inserting in the emitter lead. So if you are taking a diode here, as it is of the same material, the same change you are also expecting this forward bias diode. But here you see this is plus and minus and this is plus and minus. So that means change is same here, same change is occurring here, but the change in the diode is opposite to the change in the VBE. So the net change is equal to 0. That means whatever the change you are expecting in the VBE, that will be compensated by the change in the diode. The same change you can expect because you are taking the same material for the transistor and the diode. So in this way, the change in VBE can be compensated using a diode here. So diode compensation for VBE, this is the circuit. And here in the emitter circuit, you have used the diode. The same thing you can do it in the other way also. So if you take this circuit, you take this circuit here. This circuit is nothing but a voltage divider bias. R1, R2 is nothing but a voltage divider bias. RC is nothing but a collector load resistor. RE is emitter resistor here. Now same thing, you are using the diode here. In this circuit also, you are using the same material for the transistor as well as the diode. Either you can take germanium or silicon. And here what happens here? Now, if you are taking here, this diode is also forward biased here. This is the diode is forward biased here. The voltage across the diode is VD. The voltage across the resistance is R2 here. We are going to calculate what is IE first. What is IE? The emitter current IE is equal to the voltage at the base minus VBE. So you can say VB, this is the base voltage minus VBE divided by the emitter resistance RE here. This is RE. This VBE will be either by diode voltage drop, it will be 0.3 volts for germanium and 0.6 or 0.7 for silicon diode. So it is very less. So what is VB here? The voltage at the base. The voltage at the base with respect to ground is equal to VB is equal to diode drop plus resistance drop here. So you can say here this is VB. So IE is equal to, in the place of VB I can write down this is VD plus VR2, that means voltage across the resistance R2 minus VBE divided by RE. This is divided by RE, right? So this is the diode voltage drop and this is nothing but the base to emitter voltage. This is the transistor drop and this is the diode drop. They are actually with the same material. As the material is same, the change in this voltage drop across the diode is same as the voltage for the base to emitter junction. So this drop is compensating this drop because this is plus and minus and this is plus and minus. So the change in the transistor can be compensated by the change in the diode. That is the reason. So the transistor voltage, that is VBE, can be compensated by the drop across this diode VD. Now you can say VD and VBE, they are, suppose if VD increases, VBE decreases. So the changes are in opposite direction. So they are tracking with each other. So you can neglect the effect of these two. So finally you can say your IE is equal to VR2 divided by RE, approximately equal to, what is IE? Emitter current. Emitter current is nothing but the almost collector current. So this is approximately equal to IC. Then I can say your collector current is actually depending on only VR2. The change in the diode voltage is actually compensating the change in the collector transistor voltage. So these two changes are actually in opposite direction. That's why IC is independent of this VBE and VD. Only IC depends on VR2. So in this way you are compensating the VBE with respect to temperature. So if temperature changes, VBE also changes and VD changes. But these two changes are in opposite direction, the net change is 0. IC should be independent of the temperature. This way we are compensating the change of collector current here, because collector current is a function of these two parameters, Ic naught, VBE and beta. So now what we do is, once you know this diode compensation techniques for VBE, I would like to tell you how the Ic naught can be compensated using a diode. Now let us see the compensation against variation in Ic naught. So I told you your collector current Ic is a function of Ic naught, VBE and beta. Just now we have seen the compensation techniques for this VBE using the diodes. Using the same diode, let me explain how this Ic naught will be compensated. So you have to take once again the voltage divider bias. Voltage divider bias means biasing will be provided using the resistors R1 and R2. And this is the common emitter configuration. Emitter will be grounded. Collector load will be the RC, and you are taking the output at the collector. VCC will be given for the biasing purpose. And this is R1 and this is R2. And let it be the current through this one is I. The current through the base terminal is IB, base current. So this is the transistor Q, which is in the active region. And we have taken the most popular configuration, that is voltage divider bias. Friends, remember, in future also you have to remember this circuit very well, because the common emitter configuration is the most important configuration. That too, the biasing technique, the most popular biasing technique is self bias or voltage divider bias. Now, here the only one change is, I would like to compensate the variation in Ic naught using a diode. Now, let us take a diode in the place of R2. In the place of R2. So, this is the diode which is in the reverse bias. So, that I am taking a diode here. And the current through the reverse bias diode is I naught. Reverse saturation current here, I naught. And I already told you, you have to select the same material for the construction of the transistor and diode. Either you have to take silicon or germanium, but you have to take only one type of material for the both devices, transistor as well as diode here. Now from this immediately you can understand how this compensation can take place. Here the total current is I here, out of which I naught is actually going through this diode, and this is IB. So I can write here IB is equal to base current is equal to total current I minus I naught. I minus I naught. I naught is nothing but the reverse saturation current. That means the current in the reverse biased condition of a diode. So once you know this IB is equal to I minus I naught, and already you know the collector current IC in the common emitter configuration is equal to IC is equal to beta times IB plus beta plus 1 times the reverse saturation current IC naught. And in the place of IB, I can substitute this. IC is equal to I minus I naught into IB, I minus I naught into beta, plus beta plus 1 times ICBO, that is ICO. If beta is very, very greater than 1, then I can neglect this one here. Therefore, I can say IC is equal to beta times I minus beta times I naught plus beta times IC naught, because 1 is neglected here. You see, what is I naught? I naught is nothing but the current in the reverse bias diode. This is I naught. And what is I naught? IC naught? Reverse saturation current in your transistor. So, here what happens? If temperature increases, IC naught increases, that means reverse saturation current in your transistor increases, and I naught also increases, but I naught increases in the opposite direction. So, I naught increases in this opposite direction, both are opposite always. The change of this IC naught can be compensated by the change of the diode current in the reverse direction. That's why here you can say minus beta I naught plus beta IC naught, almost all they can track each other. They will be almost all equal because of the same material. So from this I can write down your IC is equal to almost beta into I. That means it is independent of the changes in the temperature. Even though temperature changes, the change in the collector current, the change in the IC naught can be compensated by the change in the diode current I naught. So this way, the diode is compensating the change of IC naught in this circuit. So that is the reason I think compensation has done against the variation in IC naught using the diode here. For anything, the most popular circuit you have to take, the circuit is nothing but your voltage divider bias or self bias or emitter bias. Okay. I hope you understood the circuit. Now, the same compensation techniques also can be done using the temperature sensitive devices. Those are nothing but the thermistors and sensistors. Let us see these compensation techniques using the temperature sensitive devices. Those temperature sensitive devices are thermistor and sensistor. So let me say clearly, what do you mean by a thermistor? Thermistor means it is a device, it is a temperature sensitive device having negative temperature coefficient of resistance. So thermistor is having negative temperature coefficient. So what does it mean? The meaning is very simple. If you are taking the graph between the resistance and the temperature on x-axis and the resistance on y-axis, with respect to temperature, the resistance goes on decreases. So if the temperature increases, resistance decreases means it is a negative temperature coefficient of resistance. It is property. The symbolic representation of the thermistor is RT, and it should have a circle like this. It is RT, thermistor. So the property of the thermistor is if temperature increases, resistance decreases. This property of the thermistor, that is resistance decreases with temperature, can be used for the compensation purpose. So let me explain how it is actually happening here. See, if you take this circuit, it is a voltage divider bias having the collector load resistance RE, R1 and R2 as usual. Now, where I have to put my thermistor for getting this compensation? So, let us say if the R2 is replaced with your thermistor, this is a thermistor, let me say it is a thermistor RT. So, R2 is replaced with the thermistor like this. I would like to explain you. Now, if temperature increases, because I have to check the temperature variations, if temperature increases, what happens? Temperature increases means resistance decreases. It is the property of a thermistor. So, thermistor property is if temperature increases, resistance decreases. That means RT decreases. If RT decreases, the voltage across this one, let it be the voltage is V2. This V2, which is actually forward biasing this junction, decreases because the resistance decreases here. If the forward biasing of this input junction decreases, automatically IB also decreases. So if input current decreases, output current also decreases. So if temperature increases, RT decreases, then V2 decreases, IB decreases, then automatically IC also decreases. So because of the temperature, whatever the rise in the collector current here, that rise will be decreased because of the property of the thermistor here. So very simple, you have to place the thermistor in the place of R2 or parallel to this. Even if you are taking a resistor R2 here, and this is as usual, you can put your resistor R2 here also. This is R2. That means you are placing a thermistor in parallel with your R2. The net resistance decreases because it is a parallel combination of the two resistances. So this is the way of compensating the rise in the collector current with the thermistor property. Okay, I hope you understood this. Now let us think once again, what is the next place for putting this thermistor here? Suppose if you take this second diagram here. In this diagram, where I have to put the thermistor? In the place of R1 or in the place of RE, in the place of R2 or in the place of RC? Definitely, just if you remember here, and if you are putting parallel to this RC, suppose for example, if you are taking a thermistor here, this is the thermistor, this is the thermistor. Thermistor is having a negative temperature coefficient of resistance RT, and if you are putting parallel to this RC here and connecting here, then also the compensation may take place. So how it is? Now let me explain. If temperature increases, by property of the thermistor, RT decreases. If RT decreases, maximum current will flow in this path. Maximum current will come in this path. So maximum voltage may be induced across RE. So VRE, voltage across the emitter resistance, increases. If VRE increases, it is a negative feedback. That means the voltage across this resistance RE actually reverse biasing this input junction. Then automatically the forward biasing decreases. Then IB automatically decreases. If IB decreases, input current decreases means output current will be automatically in the decreasing manner. That means the range of IC with temperature can be compensated by the thermistor property. So finally, I can conclude, my dear friends, the thermistor is a device which is having a negative temperature coefficient of resistance. That property we are using very simply in this voltage divider biasing circuit. The first location is across R2 you can put the thermistor, or otherwise you can put your thermistor across RC here and connect it to the emitter like this. So this is the way of actually compensating your rise in the collector current due to temperature by using your thermistors. Thermistors generally you can use the application of this thermistor in your houses also, in your fridge. It is a temperature controlling device. Whenever the temperature is not achieved up to the set point, it is going on changing this. So here one more device is there which is just opposite to this thermistor, that is nothing but the sensistor. Sensistor means very simple. If you are taking the sensistor, it is having positive temperature coefficient of resistance, whereas your thermistor is having negative temperature coefficient of resistance. So what is the meaning of positive temperature coefficient of resistance? If you are drawing a graph between this RT as well as the temperature, this is the temperature on x-axis and RT on y-axis, as it is a sensistor, I can say RS. So here it is having a positive temperature coefficient of resistance, means if temperature increases, resistance also increases. This is the curve you are going to get, exactly opposite to your thermistor. Now using this property, I can compensate the rise in the collector current due to the temperature. So what may be the best location? Because you see, in this voltage divider bias, already this location, that means across R2 and across RC completed. It is the best way of remembering this. What are the other possible locations here? One is across R1 and across RE. So let us see. Across R1, I am putting the sensistor now. So this is a sensistor I am putting here across R1. So this is RS. Sensistor I am putting here. Now let us check what happens here. If temperature increases, if temperature increases, your Rs also increases because it is a positive temperature coefficient resistance. If Rs increases, the current through this R2 decreases because you see it is maximum resistance. So, in the maximum resistance you can put here, then the current through R2 decreases. So, IR2 decreases, IR2 decreases. If IR2 decreases, the voltage across this R2 decreases. So, if VR2 decreases, forward biasing of the diode decreases. That means IB decreases, input current decreases, IB decreases. If IB decreases, automatically the output current also decreases. So, this is the way of understanding. What you are seeing, you are simply putting your sensistor in the place of R1 or parallel to the R1 also you are putting this because the resistance will be more here. If the temperature increases, resistance also increases. So, the current through R2 decreases, the voltage across R2 decreases, forward biasing of the input junction decreases, then automatically the collector current also decreases, then the output decreases. So, this is the way of compensating this. Next one, friends. So, already this portion is also completed. We have completed this RC and R2 for your thermistor and for the sensistor across R1. So, what is the next portion here? Next portion is nothing but your RE. So, the next one is you can put your thermistor RE across this. This is sensistor across this. This is RS. So, if you are putting like this, once again you can say that if temperature increases, your IC increases automatically. The increase in IC can be compensated by using a sensistor across this RE. So, automatically RE increases. If RE increases, RE increases. If RE increases here, so the voltage across this one also increases. So, biasing voltage increases. So, you can say that VRE increases. This voltage across this RE is nothing but a negative voltage that is given to this input. So, that means biasing decreases, forward biasing decreases, means IB decreases. If input current decreases, IC also decreases. So, this is the way of understanding the compensation using thermistor and sensistor. So, in this class, I told you the compensation techniques. The reason for going for this compensation techniques is, in the stabilization techniques, using your fixed bias or character to base bias or self bias, which is also called as voltage divider bias. In all these techniques, fixing of operating point is excellent. And we have taken care of the variations of the IC with respect to reverse saturation current and VBE and beta. But only one major problem in those biasing techniques is feedback problem. The net gain decreases, the net output decreases. So, as the amplification of the signal decreases, then we are going for this compensation technique. In the compensation techniques, there is no loss of the signal. So, this compensation is actually provided by our devices. Those are nothing but your diodes, transistors, as well as temperature sensitive devices like thermistor and sensistor. I hope you understood the compensation techniques using diodes, transistors, and as well as with temperature sensitive devices. Okay, thank you.